we explore how microservices work together in our system. Let's begin with the Service and Device Registry. This microservice manages two catalogs, one for services and another for devices. A data.json file stores basic information like service names, URLs, and also device-specific settings, such as device ID, name, thresholds, and ThingSpeak configurations. The main code is structured as a class that implements HTTP methods like GET, POST, PUT, and DELETE to interact with both catalogs. Whenever a microservice or device starts up, it communicates with this registry. For example, a microservice sends a POST request to the service catalog to register its identity, broker address, and type. If it's already there, the system simply acknowledges it. Otherwise, the new entry is saved. Sensors can also query the registry to find which MQTT topics they should use for publishing data. This entire service is built using CherryPy, allowing us to expose all these operations through a RESTful API. Sensor Data Simulation Microservice. This section covers the sensor simulation microservice. It starts by reading device info from a config.json file, things like name, ID, location, type, and thresholds for temperature, light, and soil moisture. A class called deviceInfo randomly generates sensor readings, along with a timestamp and device ID. Before publishing, the service tries to register itself in the device catalog. If it's already there, it updates its info. Otherwise, it adds a new entry with a POST request. Then it fetches the MQTT broker address and topic from the service catalog. And finally, it starts publishing data periodically to a topic via MQTT. This setup makes the service behave like a real sensor inside the system. ThingSpeak Adapter Microservice. This part focuses on the ThingSpeak Adapter Microservice, which serves as a bridge between our IoT system and the cloud-based analytics platform, ThingSpeak. At startup, the service reads from a config.json file, or environment variables. This includes the MQTT broker address, REST endpoint for ThingSpeak, and the specific topic it should subscribe to. In other words, it knows exactly where to listen for incoming data and where to forward it. Once running, the service acts as an MQTT subscriber, listening to the topic where sensors publish their data. Every time a sensor, like temperature or soil moisture, sends a message, this microservice captures it, parses the JSON payload, and prepares the data for upload. Next, the data is formatted and sent via HTTP POST to the appropriate channel on ThingSpeak. ThingSpeak stores the data and displays it in clean, real-time charts, allowing us to visualize trends such as humidity over the week or temperature fluctuations during the day. But that's not all. ThingSpeak Adapter also exposes a set of REST APIs so that other microservices like TimeShift or Telegram bot can retrieve past data or averages as needed. For example, the TimeShift service may use this to pull a week's worth of data and predict conditions for the upcoming days. Overall, this microservice allows us to stream sensor data in real time, store it securely, display it visually, and even make it available for downstream analysis. It's a key component in connecting our live sensor network to a scalable cloud-based data platform. Sensor Control Microservice. This section is about the Sensor Control Microservice, which is in charge of analyzing incoming sensor data and checking whether the environmental conditions fall outside the safe range, either for the plant or for the home. At the start, it loads a file called home_environment_config.json, which contains the temperature and humidity thresholds for both summer and winter. It also reads the necessary URLs for accessing the service and device catalogs. Once the service is running, it first registers itself in the service catalog. Then it subscribes to the MQTT topic where sensors are publishing their data. Every time new sensor data arrives, this microservice receives the message and immediately fetches the corresponding thresholds for that device from the device catalog via REST. It also determines the current season, for example, winter, and loads the relevant home thresholds from the config file. Then, it compares each sensor value, like temperature or soil moisture, against both sets of thresholds. If a value is too low or too high, the service generates a warning message. These messages say things like, soil moisture too low for device A, or temperature too high for device B. Finally, the warning messages are published to the control topic via MQTT. Time Shift Prediction Microservice. Its main job is to predict future environmental conditions, basically saying what the temperature or soil moisture might look like in the next few days, based on past trends. At startup, it reads the config.json file, which includes REST URLs, the MQTT broker, how many weeks of past data to use, and the topic to publish alerts to. It then sends a REST request to the device catalog to get a list of all registered devices. For each device, it contacts the ThingSpeak adapter to fetch historical temperature and soil moisture data. The data is cleaned and loaded into a data frame. Then it fits a linear regression model to predict values for the next 7 days. Each prediction is compared against the device's defined thresholds, both minimum and maximum. If any predicted value falls outside the safe range, it generates a warning message. For example, soil moisture for device A will be too low on day 3. These alerts are then published via MQTT on the ALARMS_TOPIC so that other services like Telegram bot or actuators can respond if needed. One unique feature of this microservice is that it only runs once per week. Using a flag file, it checks if it has already run during the current ISO week. If yes, it waits. If not, it runs the full prediction cycle and then pauses again. So overall, TimeShift acts like a smart forecaster. It looks at the past, detects patterns, and warns the system in advance, before anything goes wrong. Telegram Bot Microservice. In this section, we have the Telegram Bot Microservice, the one that connects the system directly to the user. In its config file, we specify the Telegram bot token, REST URLs to access ThingSpeak adapter, and the MQTT topic for receiving alerts. This microservice works with both MQTT and REST. It subscribes to a specific MQTT topic to receive alert messages published by other services, like sensor control or time shift. Once it receives a message, it formats it into something user-friendly, like alert. Temperature for device B is expected to be too high tomorrow. At the same time, the user can also send commands to the bot, like asking for the latest data or a weekly summary. In that case, Telegram bot uses REST API calls to fetch the needed data from ThingSpeak adapter, summarizes it, and sends the response back to the user. The replies can be plain text, data tables, or even links to ThingSpeak visualizations. This microservice plays a key role in user experience. While other services handle data and communication, Telegram bot acts as the human-facing layer, bridging the gap between raw data and practical insight. So in short, it's a two-way bridge. It delivers automatic alerts from the system, and it also responds to the user's manual queries in a clear and helpful way. Project Flow with Docker. In this part, I'll walk you through how the entire system is launched and coordinated using Docker. We use Docker Compose to manage all our microservices, making sure each component runs in an isolated, controlled environment, but still communicates smoothly with others. From the terminal, we run Docker Compose up, build. This tells Docker to first build the images for each microservice, based on the Docker files, and then launch them in the order defined in the docker compose.yml file. At first, we see that core services like the message broker and service registry start up before the rest, because other services rely on them to fetch connection details, topics, or service endpoints. Then, one by one, the other services join in. Sensor simulation, ThingSpeak adapter, sensor control, time shift, and finally the Telegram bot. Each service prints its own logs, which we can see right there in the terminal, so we know what's happening live. For example, we can see when the sensor publishes data, when time shift runs its predictions, or when alerts are generated and sent over MQTT. If we ever want to check logs for a specific service individually, we can use Docker logs, container name, or even jump into the container using docker exec -it container _name bash. One of the key things about this setup is that services automatically discover each other using dynamic registration. They fetch URLs and topic names from the service catalog, instead of relying on hard-coded settings. For example, the sensor fetches the MQTT broker address dynamically, and TimeShift knows where to get past data using REST. With this setup, everything feels like it's alive and connected. Data is generated, analyzed, predicted, and delivered to the user, all starting with just one command: Docker Compose up. This not only makes development and testing easier, but also allows for smooth deployment in real-world environments, whether on a server, cloud, or local machine. Using Docker Compose, we've built a clean, modular system where each microservice handles one responsibility and communicates through MQTT and REST. We don't have to manually start services or configure IPs. Everything is automated and self-discovering. This architecture is scalable, easy to maintain, and perfect for deploying across different environments, local or cloud. Another useful thing about using Docker is how easy it becomes to scale or replace individual services. For example, if we want to test a new version of the sensor microservice, we can simply rebuild just that container without touching the rest. Also, we can run multiple instances of a service, like having 2 sensor simulators with different configs, just by adjusting the compose file. This Telegram bot is an intelligent system for monitoring indoor plants. By registering each plant, users can continuously track key parameters such as temperature, humidity, and light. Optimal ranges are predefined, and the system compares actual conditions with these thresholds. If any value goes beyond the limits, the bot instantly notifies the user through Telegram. It also supports adding unlimited plants, making it simple to manage multiple species at once. In this way, the bot provides an effective and reliable solution to ensure the health and vitality of indoor plants in everyday life.